Hello, everyone. All right, welcome back to Grade 12 University Physics here with Mr. Stone. So, this is our last lesson of the course. It's going to be a pretty big lesson, but not very deep because this is a huge field, okay, of what we're going to call nuclear physics. So this is the study of the nucleus itself, and this gets very strange, and the forces are not like we would expect, and really when it comes down to it, we really don't understand nuclear physics truly, because you got to remember that when we have an atom, let's say, right, when we talk about atoms, we talk about how atoms interact with each other, the electrons. We can kind of talk about how those things work. We have Schrodinger's equation to understand how that works. We can understand the what we call quantum electrodynamics of the electrons. But the nucleus is much smaller, right? It's down to the femtometer scale. That's 10 to the negative 15 meters. So we're scaling down another 5 orders of magnitude, which means to interact with these things, we need to really increase the energy. Remember, we talk about that idea that to get down to the resolution of atoms, we need to use X-rays. Right? And X-rays already are quite high powered. Now, to get to the resolution of atoms, we even have to go much higher energy levels. So we have to use things like particle accelerators to get things up close to the speed of light and crash them into each other, and hope that their nuclei interact, and we can see what happens. We can basically cause a nuclear car crash and then try to see what happened in the car crash by looking at the pieces, the crash afterwards. That's basically how a particle accelerator works. Take protons, smash them into each other, a bunch of stuff flies off. We try to figure out what happened. So, not only is it incredibly small, which requires large amounts of energy. Remember, lots of energy interacts with things and pushes things around and changes things. And these are very quantum mechanical. The other thing that's difficult about this is they're heavy. Right? These are 2,000 times heavier. A proton, for example, is 2,000 times heavier than an electron. So these things have mass. They're quite a lot of mass. So things get really strange. Okay, so we're going to do a quick little introduction to some ideas, some useful things to know about how nucleons interact with each other, how they deal with, and some of the applications, like nuclear decay, radioactive dating, which is interesting, carbon dating, stuff like that, and nuclear fission and fusion. Yeah, that's going to be basically what we're going to talk about. So again, so far we've talked about electrons and their quantum mechanical behavior, right? And if you go closer and closer down, right, things get even weirder. And remember, we said that I just talked about this, that the nucleus is this tiny little thing. For example, it would mean that if you had a classroom, the nucleus would be a grain of sand in the middle of it. And that grain of sand contains the entire mass of the classroom. So that gives you an idea of density. If the classroom's mass is entirely stuck in that tiny little grain of sand, the rest of the atom is empty. Right? The electrons are whizzing around each other. Because they're so small, they're fighting with that by the uncertainty principle, and they have to fight against each other as well because they're charged. So they end up forming these sort of empty space full of just basically electrostatic fields. But the mass, the actual stuff of atoms, is contained just in that nucleus. Now, the things that govern the interaction of inside the nucleus, right? That's weird. We have to start talking about the strong nuclear force. Right, so far everything we've talked about in this course has been really gravity pulling on things and the electrostatic force pushing on things or attracting things. We've never talked about the strong nuclear force because it's very strange. Or even the weak nuclear force. The weak nuclear force is even weirder. And it's all about the fact that atoms themselves, right, an atom of something, its properties are defined, or what it is really, like a carbon atom is a carbon atom because it has 6 protons. Okay? If I take a proton away, I now have nitrogen. And we know that the chemical properties of nitrogen are very different than the chemical properties of carbon. One is a gas, diatomic gas usually. The other one is basically like soot or your pencil lead. Right, so I can change pencil lead into a gas by removing a proton. Right? And that's not, you can't just go in there with tweezers and grab a proton. That's a very strange, very difficult thing to do. But when we're talking about nuclear physics, rearranging nucleons and moving things around really talks about, changing elements. When we talk about nuclear decay, elements transmute into new elements. This brings back the old alchemical dream of transmuting lead into gold. But what's fascinating is that the alchemist just got it wrong. Everything ends up at lead, actually. Lead-210 is one of the most stable nuclear isotopes. So things usually just decay down into lead-210. And that's the weird thing about nuclear physics is, this stuff actually happens. Atoms transmute, atoms change. Atoms lose protons. Their protons and neutrons switch places. All kinds of strange things happen because they're governed by these very strange forces called the strong and weak nuclear force. And we end up with these weird Feynman diagrams. Like this is the interaction between, this is what happens if a proton and a proton collided, let's say in a particle accelerator. You have some very strange things happening. You have these gluons being formed. You have gluons decaying into a down quark and an anti-down quark, and we have these mesons being formed, these mesons here, and these muons being formed, and anti-muons from this decay of a weak interaction. It's very strange stuff. Okay, and as you can see, what we're talking about the internal structure of these things. A proton, for example, is made up of 3 quarks. An up, and a down quark. What the heck is a quark? Well, we've seen the standard model. Hopefully, you've seen in the previous lessons that there's 6 quarks: up, down, charm, strange, top, bottom. And they're just basically different flavors of quarks. And notice there's also these colors as well. There's color change happening as well. They're not actually flavored. They're not colored. They're just words to define quantum mechanical properties, quantum numbers, but not just binary quantum numbers. Anyways, I'm getting confused. We're getting way too far off topic here. Anyways, let's just talk about something we can really concretely, experimentally see, which is nuclear decay. So nuclear decay basically was discovered in the beginning of the 20th century, when chemists basically took newly discovered things like pitchblende, which contains uranium, and they put it on some photo paper, let's say, and stuff came off of it. There was some sort of things coming off of this material, and they called them things like N-rays and X-rays as well. Röntgen called it an X-ray. And all this stuff was coming off of these materials. And from our modern view, there's 3 different types of things that come off of these things. There's alpha decay, beta decay, and gamma decay. Right? Let's go through these different ones. So alpha decay is what happens when a very large nucleus, so it's got a lot of protons and neutrons in there. Because of its size, it can actually lose some particles. It can actually become a more stable version of itself by giving off some of its things, because it's basically you're holding together, 200 plus protons and neutrons together with a strong nuclear force. The gluons, the strong nuclear force, these gluons are holding it all together into this thing, and they can exist in these quantum mechanical levels of whatever. But every now and then, it can actually jump out of these. Some protons and neutrons can actually just fall out, which is comes back to an interesting quantum mechanical idea of quantum mechanical things, like a wave function, let's say. A quantum mechanic, something that behaves according to quantum mechanics, there is a finite probability that it can jump over a wall or through a wall, a better use of the word here. So let's say there's a potential well. The way that we typically define these is that we have the electrostatic potential, right, of the protons wanting to fight each other. But then as you get close enough, we end up with this potential well on the inside. Sorry, let's just draw this a bit better. It's kind of good. This is what the inside of a proton looks like. So you have all your protons and neutrons in here inside the nucleus. They're all contained within this, and they're held together here by the strong nuclear force. And notice I have it straight across. That's one of the fascinating things about the strong nuclear force, is it's sort of stable. It sort of stays the same. That's what makes it really strange. If I try to pull apart a proton, like two protons, or two positive things, they're going to want to repel each other. And the farther away they go from each other, the force reduces, or the strength of the potential energy between them reduces as 1/r. In the strong nuclear force, when I try to pull things apart, it doesn't change. So this is the weird, if I try to take two quarks and I try to pull them apart from each other, at some point, it becomes energetically viable for, instead of going out farther apart, they'll actually generate a new quark anti-quark pair. It's called a meson. It generates a new thing. Okay, so as we're putting more energy into it, that energy that we're putting into it gets converted into mass by E equals mc squared. See what I mean? These strong nuclear force, this is strange stuff. But it gets back to the idea here. So we have these protons and neutrons in here. So we have this barrier, this potential well here. And what's fascinating about quantum mechanics is it says that there's a finite probability that something can be on the other side of that wall. In quantum mechanics, if you tap on a wall enough times, there is a non-zero probability that your hand will actually go through the wall, because your hand is made up of quantum mechanical things, electrons, and so is the wall. Now, the probability of that happening is, it probably will never happen in the lifetime of the universe, but it's non-zero. There's not a zero probability that you will just go through the wall. There is a finite probability. It's incredibly, incredibly small, but because it's quantum mechanical and probabilistic, there's a chance that it could go through the wall. Now, in this quantum well here, there is a finite probability that protons or neutrons could actually be on the other side. And once they get to here, whoop, the electrostatic potential will push them away. Now, it's not very likely that a proton by itself will be able to, just magically jump out, or a neutron by itself. It turns out that the most likely thing, the highest probability thing that will be able to just be emitted, turns out to be a helium nucleus. Because a helium nucleus is so stable, something to do with something called magic numbers. I don't exactly understand, but there's something to do with the stability of the helium nucleus that allows it to have the highest probability of being on the other side of the well. And then once it jumps out, it's gone. So alpha decay is basically this weird interaction of the strong nuclear force. Once we get these very, very large atoms, there's the possibility of instability within the atom, and there's a finite probability that protons and neutrons will be able to just pop out, jump out of the potential well. And that's alpha decay, and that's what this helium nucleus is coming out here. So this is radium. This is radium-86, and it's got a mass of 222. Once it jumps out, it's reduced its atomic number by 2. So it's gone from 86 to 84. We've changed radium into polonium. And not only that, we've removed -2 protons and -2 neutrons as well. So we've reduced the mass by 4. So that's where our helium nucleus is coming from. So we've managed to transmute radium into polonium using this strong nuclear force. Now, the things that come off here, this is a helium nucleus, right? So it's very heavy, relatively speaking, nucleus-wise speaking. It's very heavy. They travel quite slowly. So for that reason, they're quite easy to stop. You can stop them with a couple of sheets of paper. They are quite dangerous in terms of what they can do to you. They're not safe in any sort of way. They can do strange things to your DNA and stuff like that. So not very nice for us, but they're quite easy to stop. Beta decay is slightly different here. This is when an electron or a positron and a neutrino is released from a nucleus. And this happens from when a neutron changes into a proton. And this happens because of the weak nuclear force. This is a strange thing that happens here. So let's say we have a proton, a neutron. So a neutron consists of an up, a down, and a down quark. That's what this conglomeration of quarks is, what we call a neutron. Now, what can happen is sometimes one of these down quarks will magically, not really magically, but there's a probability that this down quark is able to, kind of strange here, one second. Sorry, so there's like a finite probability that this down quark can actually decay into an up quark. It can transmute, it can change into a different flavor of quark. And to do that, it has to give off a weak boson, a weak interacting thing. And that weak boson will then, it can't exist by itself. These bosons don't exist by themselves, but they'll themselves will break down into an electron and an anti-neutrino, an anti-electron neutrino. Okay, we talked about this already, I'm pretty sure. So this is what happens in beta decay. There is a transmutation, this change that a neutron becomes a proton. So let's say something like nitrogen can become carbon because one of the neutrons in nitrogen turns into a proton and it changes it. And the important thing here is these electrons that are given off. These are called beta particles. They're just electrons. Now we can do the opposite, where a proton becomes a neutron, and that gives off that'll give off a positron, an antineutrino. The sort of the opposite version of these things. And yes, this is very strange. Okay, we're talking about nuclear physics here. Things get weird. And the fact that antineutrinos kind of travel backwards in time. Let's not worry about that. Anyways, so these travel very, very quickly. They're very, very fast, and they're pretty hard to stop. Well, relatively hard to stop. You can stop them with a couple millimeters of like plastic, of urethane or something like that. And again, it's the weak nuclear force, right, that causes all this strangeness to happen. And the last one we want to talk about is gamma decay. And gamma decay is from when we talked about this already, but when the nucleons inside rearrange themselves. It's very similar to what happens when energy levels in an atom give off photons of light. Energy levels inside the nucleus give off photons of gamma radiation, or high energy light. They travel at the speed of light. Really hard to stop, right? Because it's light. And it happens due to the rearrangement of nucleons. All right. So even though it says here that this nucleus is still here, the internal structure of the nucleus has changed slightly. It's gone to a lower energy state, and the energy difference between them, right? There's some energy change here, and that's going to be equal to, right, the frequency of light by Planck's formula there. Okay, so alpha, helium, beta, electrons, gamma, light. Now, what's interesting about this idea that radioactive materials break down is that because of that idea that there's this probabilistic chance that stuff will just fall apart, right? All these things are run by probability. It means that the amount of stuff that's left dictates the rate at which it's falling apart. The more stuff there is, the more decay there is. They're proportional. The rate of change of decay, so we could say the rate of change of the mass, let's say, is proportional to the mass itself. Okay, and this becomes what we call a differential equation, right? We can really say that the way they write it in calculus would be that this is equal to minus kn. Okay, so the rate of change of the stuff as a function of time is equal to the function itself, n of t. The rate of change of the function is equal to the function multiplied by some negative coefficient, and that works out to an exponential decay. Okay, some a e to the minus k t function, or a is the amount of stuff we had to begin with, or maybe I could say n naught. Okay, so that's my function that satisfies. That's my differential. Oh, look at that! We just did a differential equation. Okay, we just did first year calculus. We just did a differential equation. We solved the differential equation. Hopefully, people here who are taking calculus will appreciate that and see how that worked. Anyways, okay, so one of the interesting ones is carbon-14. Carbon-14 is a type of carbon that exists in us. Every living thing has carbon-14 in them. It's what happens when nitrogen is converted to it by hitting some sort of cosmic ray. Some stuff from space hits a nitrogen in the atmosphere, turns into carbon-14, and we breathe it in. Once we breathe it in, it gets put into our bodies. We either we breathe it or we eat it. Somehow it gets attached into our body. So our body, when we're living, while we're breathing and eating and doing normal things, we have a certain percentage of our body is made up of carbon-14. And when you die, you stop absorbing stuff. So once a living thing dies, the amount of carbon-14 starts to decay because carbon-14 has a certain amount of stuff decaying in it. It's a radioactive element. I think it's a beta decay, but it decays every. So the idea here is every 5,730 years, half of the stuff will be gone. So if there's a certain, let's say it's 100 grams of carbon-14 in you right now, 5,500 years from now, your corpse, your whatever is left of you, will have only have 50 grams of carbon-14 in it left. So if we're able to take something and measure how much carbon-14 is in it, something organic, something living, that was living, pardon me, or something that had something living in it, something like cloth, fibers, things like that. If we're able to measure the amount of carbon-14 in it as a percent of how much there should be in it, we can calculate how old it is. So we can use radioactive dating to take something and actually find out how old it is. So the amount of carbon-14 left in some fossil or dead organism follows this exponential equation here. This is an exponential decay. The amount of stuff that's left after t years is equal to how much we have to begin with, A naught, multiplied by a half to the power of t, the amount of years, divided by the half-life. Right? We're basically multiplying by a half to the power of how many half-lives you've been through. Okay, hopefully you remember your grade 11 exponential functions unit to see, and hopefully maybe you've even seen something like this before. Now, let's say we have a material, and I calculate that it has 37% of the carbon-14 left. How old is it? So if we take our formula, and I divide both sides by A naught, I can get this fraction, 0.37. And I know that the half-life was 5,370 years, annum years. Now I just have to solve this for t. Now this can be a little bit tricky, but hopefully you guys have done logarithms, and you know that if I take the log of both sides, or the natural log of both sides, the ln of both sides, I can then take my exponent and bring it to the front. The exponent becomes multiplied. If I take the natural logarithm of this exponent here, the power, the exponent then comes out as a multiplication in front. And I can divide both sides, and I end up with 7,700 years. Okay, so we can use this very practically to calculate how much stuff is left, just due to the radioactive decay, because it's determined by a probabilistic thing. Okay, so next, really cool here, energy. Now remember, energy and mass are equivalent. E equals mc squared. That's a very important thing we have to remember here. Now, so what that means, if I measure the mass of a nucleus as it's held together, it always ends up being less than the protons and neutrons that make it up. How is that possible? How is it possible that I can combine a bunch of protons and neutrons together and come up with less mass in the end? Where is that mass disappearing to? Anyone have any ideas? Okay, let's do an example here. So if I take uranium-235, it's going to be made up of 92 protons and 143 neutrons. So according to my values I have here, if I just multiply them out, I'm going to get a mass. This is individually. If I just take 92, if I somehow have this like nucleus cup, and I take 92 protons and I stick them in there, and I take 143 neutrons and I put them in there, and I stick that on a scale, it's going to weigh 237 basically atomic mass units. Now, that is a difference of almost 2 atomic mass units compared to the actual mass of the nucleus. If I take all those protons and neutrons and I stick them together to make a uranium-235 nucleus, it weighs a lot less. Where's that mass difference? This is a mass defect. Where's that energy gone to? Where's that mass gone to? Anyone? It's gone to energy to hold it together. That's the energy that's required to keep it together. That's the binding energy, we call this. This is the energy that holds the nucleus together. So there's, we can measure it as a mass here, or as a mass equivalence. That's equivalent to 1.74 giga-electron volts. 1.47 giga-electron volts is holding the mass together. We call this the binding energy of our atom. Now, important thing here is if I take every element on the periodic table and I calculate this binding energy, this difference here, and I divide it by the number of nucleons that are available, and I calculate what we can call the binding energy per nucleon. So that's the total energy that holds the whole thing together divided by how many we have in there. So how much energy is holding each nucleon or proton or neutron? Nucleon means proton or neutron. How much energy is there per nucleon in each element? If I graph that, I end up with this fascinating graph here. There is a maximum energy at iron, around there, nickel, iron, whatever, 56-ish. Mass number 56 that has the maximum amount of binding energy. And everything else To the right of this, anything bigger, it's getting down. The larger and larger I get, the less binding energy there is holding it together. And in the opposite way, if I get smaller, there's less binding energy holding it together. You may be thinking, okay, so what is the point of all this? So, for example, our previous example of uranium, it works out that there's a binding energy per nucleon of 7.4. So 235 is about here, so it's about 7.4. Whereas iron has something like 8.3. Okay. Now, again, what does that mean? Now, this is the important part here. What it means is that larger nuclei will possibly want to go, what they want to do is they want to get smaller. They want to break apart. They want to undergo fission, nuclear fission. The nuclei want to fall apart to increase the binding energy per nucleon, because the higher binding energy makes it more stable. And otherwise, opposite, small nuclei would want to combine to form larger nuclei to get more stable. And the most stable is iron. Okay, so small, and after iron, it's going to start, anything bigger than iron will want to fall apart. And everything wants to tend towards that iron magical number of 56. Okay. Now that doesn't necessarily mean that they can do this, right? There's lots of things holding this back. Typically, fission only happens on transuranic atoms, things that are larger than uranium, because nuclei usually want to stay together. But when you get really, really big, they tend to just fall apart. They fission, they break in half. And forming nuclear fusion, to get small nuclei to come together, you're going to have to overcome this incredible electrostatic repulsion between the protons, right? To get a nucleus to come together, the reason that nuclear fusion doesn't just happen by itself is that it has to squeeze and squeeze and squeeze and get past that repulsion of the two protons, or the multiple protons in the nucleus, so that they can eventually, once they get past a certain point, then they're going to come together and make something new. That's what happens in the sun, right? Hydrogens bash into each other and make helium, kind of. And this is why stars actually stop making new materials at iron. Once a sun starts producing iron, it stops working. The sun undergoes basically a nova. It explodes and it dies. Wow, we've gone a long. We've already talked half an hour here. We're not even close to being done. This is going to be a long lecture. Maybe I'll stop here actually. What's next here? Yeah, maybe we'll just stop for a moment. I'm going to make this into a 2-part video, okay? Just because we're already at half an hour. Okay? So, I'll be back in a second.